This is section 14.1, the real numbers. Okay, so we're going to go over different categories of numbers here. The first one is natural numbers. We also call these the counting numbers. The reason we call them natural or counting numbers is basically they start at 1 and then it goes just like you would count. So 1, 2, 3, 4, 5, 6, and so on. So you don't have any negatives, you don't have any decimals, you don't have any fractions, just your regular numbers, and you are not including 0. Okay, so those are the natural numbers. The next ones are the whole numbers. So what that is it's all of those natural numbers plus 0. Okay, so 0, 1, 2, 3, 4, 5, and so on. Then the next one is integers. So we're kind of working our way out here. So we start with the most specific at natural, and then all of the natural numbers are also all the whole numbers, while all whole numbers are also integers. So our integers, to add on to our whole numbers and our natural numbers, so it's all the naturals, so like 1, 2, 3, 4, 5, 6, 0, which is part of the whole numbers, and then the difference in integers is it also includes the negative version of the natural numbers, so like -1, -2, -3, and so on. So that's those ones. The next one is rational numbers, so this is where it gets a little bit trickier here. So our rationals are numbers that can be written as a fraction. Okay, so the first thing we could have is we could have just a straight up fraction. We can also have anything that's in the integers group, the whole numbers and the natural numbers. So you could have like regular numbers, 1, 2, 3, 4, because those could be written as a fraction. Like 2 as a fraction would be 2 over 1. So 2 would be a rational number. You can have decimals here, so like -0.2 is the same as -1/5. So that could be written as a fraction. 0.3 repeating is the same as 1/3. And then this one here, you can have square roots if it comes out nice. So I believe that this is the square root of 0.25. I think it's a half. I'm not quite sure on that one, but it does come out to be a nice fraction. If you did it on your calculator, you'd get a nice decimal that could turn to a fraction. Let me grab my calculator here and kind of show you what you could also do. So if you weren't sure on a number like that one there, square root of 0.25, what you could do is you could plug that in your calculator, do it, and you get 0.5. And then if you weren't sure if that was a fraction, we know 0.5 is the same as a half. But what you can do is there's this math button here. If you press that, and then the first one, FRAC, is for fraction. If you push enter there, and then enter again, it'll turn whatever decimal you had there to a fraction. So that could be another way you could double check that. But yeah, that one would end up being a half. So all of those could be turned into fractions, so those are all rational numbers. Now our irrational numbers are numbers that cannot be turned into a fraction. So we'd have weird things kind of like pi. So if you've never heard of pi before, basically what it is it has to do with circles. And it's 3.1415 and then a whole bunch of numbers following forever, and there's no patterns, nothing repeats, it's just all random throughout there. So that's called an irrational number, anything with pi. Square root of 2 is also considered irrational because the difference between square root of 2 and like say square root of 25, so if I did square root of 25, it comes out to be a nice number. If I do square root of 2, what it's going to do is it's going to give me a crazy number like this, and realistically it's going to keep going on and on and on and on forever, but my calculator can only think so hard, so it stops at a certain point, whatever it's programmed to stop at, but realistically here, square root of 2 is 1.41421, and it just keeps going and going and going and going, and it never repeats itself, and it never stops. So that would be why square root of 2 would be irrational. You might also have things here that follow a pattern, but the pattern is not necessarily like 1, 1, 1, 1, 1, 1, 1. What it's going to do is it could be like growing here, so like 0.10 and then 1 and then 2 zeros, 1 and then 3 zeros, 1 and then 4 zeros, and so on. That would also be irrational. Okay, and then the set of real numbers is all of our rationals and all of our irrationals. So what we're going to do here is we're going to fill in this chart with all of our real numbers, irrationals on this side, rationals on this side, and then our rationals are going to be broken into the different groups. So I'm going to start with the most specific of the groups. So Our naturals are the most specific numbers. Those are our counting numbers. So you'd have like 1, 2, 3. You could have like 55, 102. Anything like that that would be a positive number that you would be counting, and it would not include 0. Okay? So now when you go out to the next one there, that's whole numbers, which the natural numbers is inside the whole numbers. So everything that's in this natural numbers box is also going to be in the whole numbers box. The only number that would be in the whole numbers box but not the natural would be 0, because 0 is a whole number but not a natural number. So all your naturals and then 0. Integers, we add on the negative versions of those numbers, so like -5, -2, -12, -50, that kind of thing. So integers are all of those negative ones, the wholes, and all the naturals. And then our rational ones are where we add in like the fractions. So you could have like a half, you could have like 0.3 repeating, because that would be a fraction, that would be equal to 1/3. You could have negative fractions, so like -2/3. You can have square roots of numbers as long as they come out nice, so like square root of 25. Actually, no, not square root of 25. Let's go square root of 0.25 like we had before. Square root of 25 would actually go in this one because that would be a natural number because it would come out to be 5. Okay, so now the irrational ones. So irrationals would be when we go and take the square root, it doesn't come out nice. So like square root of 2 would be in that group. Square root of 5 would be in that group. You could also have like 2 irrationals added together, so like square root of 2 plus square root of 3. So those are both irrationals, and when we add them together, it's still irrational. You could have pi, you could have something with a pi, so like 2 pi or a half pi. Oops, half pi, something like that. You could have, we haven't seen any of these yet, but this will be what we're working on this chapter, 2 times, you know, like the square root of 2 or something like that, where it's multiplying by an irrational number. So all of those fit in that group. Okay, so for our examples here, what they want us to do is they want us to figure out which groups or which sets the number they give us belongs to, and then there could be multiple depending on where it lands. So first number there is 10. 10 would land in our natural numbers group because that would be one that we could count to. So it's in the natural numbers, also in the whole numbers, integers, and rational numbers. So we'd write all those out. So we'd go natural. And if it is in the natural group, then it's also in the whole numbers group, the integers group, and the rational group. Okay, and then the next one, negative square root of 100. Well, what I would do there is I would actually do square root of 100 and see if it comes out nice. So square root of 100 is 10, and then with the negative out front, that's like a negative 10. So it's not going to fit in my naturals or my wholes because it includes a negative, but it doesn't have any fractions or anything, so it could be in my integers group. So this would be in my integers group. And then working my way out, it would also be in my rational group. And then the next one here, again, I would probably simplify this. So 5 squared is the same as 25. So if I'm looking at 25, that would be in my natural group. So that's going to be all 4 of those. So natural, whole, integers, and rational. Okay. Some more here. Next one, this is supposed to be like 0.6 repeating. Those 3 dots mean repeating after it. So 0.6 repeating as a fraction would be 2/3, so that would not be irrational because we could actually turn it into something, and it doesn't fit in our natural, whole, or our integers, so it's just got to be the rational group here. And then the last one, square root of 17, so if I took my calculator and did the square root of 17, it comes out to be not a very nice number there, so if it does do that, not a very nice number, that's irrational. If it's irrational, it's not in any of the other groups. Okay, the next thing here, completeness property of points on a number line. So I'll just read it to you on page 601. So what that says is each real number corresponds to exactly 1 point on a number line, and each point on a number line corresponds to exactly one real number. Okay, so what they're saying there is this entire number line going to infinity and negative infinity is going to contain all of the real numbers. So you've got your regular numbers like 1, which would be natural. You add on your 0, would be your wholes. You add on your negatives, that gets you to integers. And then we know in between all of these, there'd be like fractions, like a half, negative a half, that kind of thing. You could also have decimals in between there as well. Your irrational numbers would also be somewhere on this number line, so they're just kind of in between some of these numbers. So like square root of 2, I believe, is 1.41 or something like that. So square root of 2 would be somewhere between the 1 and the 2. So like say we had like 1.4 right there, square root of 2 would be just after that. So this number line is filled with all of your rationals, so just, you know, your regular types of numbers, including like the fractions, but also your weird numbers, your irrationals, are also on that number line, and that would fill it up completely. The next thing we're going to do here is we're going to be dealing with square roots and perfect squares. So if you don't have this in your notes somewhere, it might not be a bad idea to write this chart down. So basically what I did is I just went up to 15 and I squared all those numbers. So like 1 squared is 1, 2 squared is 4, went all the way up to 15 squared is 225. And then the other side of this chart is just doing like the opposite, so taking the numbers in the second column and doing the square roots of them and getting the numbers in the first column. So it might not be a bad idea to have that in your notes just as a quick reference point. You should be able to have your calculators for the test, so it probably won't be terribly important, but it can kind of help you just look at it quick and not have to use your calculator to guess and check all the way through. Okay, so what do we want to do here is it says find an approximation to the nearest tenth for each square root and then graph it on a number line. Okay, so what I would do for an approximation is I just use my calculator and I'd go, okay, square root of 10, which is 3.16, and if I want to go to the tenths, that would just be one position behind the decimal point. So 3.16 would round to 3.2. So I'm going to put a squiggly equals in there because that means approximately equal to. So approximately equal to 3.2. And then if I was going to graph this on a number line, say I had like 0 there, 3, and 4, this would be in between the 3 and the 4, closer to the 3, so I'll just put like a little point in there. That would be square root of 10. Okay? Now how this works and how we can use our chart here is square root of 10, if I look through here at my square roots, 10 would be in between the 9 and the 16. So 3 would be the square root of 9. 4 would be the square root of 16. So it logically kind of makes sense that the square root of 10 would be in between square root of 9 and square root of 16, because 10's in between 9 and 16. And it would make sense as well that it is closer to the 3, because 10 would be closer to 9 than it is to 16. Okay, so on the assignments, make sure that you graph something out like this and then label where your little square root would be at. Alright, let's try another one here. So this one is negative square root of 8. So again, on my calculator, you can put the negative in there or not, it's up to you. So negative second square root of 8. And then that would be approximately negative 2.8. So on our number line, so I'm going to go 0 there, negative 2, and negative 3. So negative 2.8 would be in between those, probably a little bit closer to the negative 3. So I'm going to do a little arrow there that says that's the negative square root of 8. And same as before, I could look down my chart and see what 8 was in between. Well, 8 would be in between the 4 and the 9 on that chart listed out for perfect squares. And that makes sense because negative square root of 4 is negative 2, and negative square root of 9 is negative 3. So it makes sense that it would be in between those two numbers because 8 is in between 4 and 9. And then it would be a little bit closer to the 9 because 8 is closer to 9 than it is to 4. Okay, so on page 602, you can try F and G, and I'll get your answers here. So F, they get that it is approximately equal to 2.4, and I'll do the graph in a second here. And G, they get that it is approximately equal to negative 4.8. Negative in there, 4.8. So for this one, our number line, have 0. Let's go 2 and 3. So our original square root was 6. So square root of 6 would be in between 2 and 3, which makes sense because square root of 4 is 2 and square root of 9 is 3. And then the other one here, we got negative 4.8, so that would do a 0 there, negative 4, negative 5, so negative 4.8 would be in between there, and we originally had negative square root of 23, and our numbers here, negative 4, that would be negative square root of 16, negative 5 would be negative square root of 25, so 23 is in between 25 and 16, closer that way, so that makes sense that it's negative 4.8 approximately. Okay, next thing here is we are looking at these numbers and figuring out if they are rational or irrational. And if they're irrational, we're supposed to figure out which two numbers it would lie between on a number line. So basically, similar to what we were just doing before, and then just figuring out which two numbers it would be between. So if I did this out here, negative second square root 59, I get a nasty number, so it couldn't be rational, so this has got to be irrational. And then I could do this two ways. I could either look at my numbers here and go, okay, negative 7 we'll go 7.7. Negative 7.7 would be in between negative 7 and negative 8 on a number line. So you could think of it that way, just kind of using your logic there. The other way you could think of it is go, okay, square root of 59 would be in between square root of 49 and square root of 64. Well, square root of 49 would be the 7, square root of 64 would be the 8, so it makes sense that it's in between there. And then the next one there, second square root 121, well, that one actually comes out nice to be 11, so if it does come out nice, then you just write rational. Okay, so we got one more example here. So this is example 10 on page 603. So it says the time t in seconds it takes for a pendulum to complete one full swing back and forth. So it looks like we got like a ball and a chain swinging back and forth is given by the equation. So we've got t is equal to 2 pi times the square root of L over 9.8, where L is the length of the pendulum in meters, and suppose the pendulum has a length of 4.9, so our length is 4.9, and then we're supposed to figure out how long does it take for the pendulum to complete one full swing. Okay, so we're just going to use this formula here. Our T stands for time in seconds, and we figured it out, or they told us that our L was 4.9. So what I'm going to do here is I'm just going to plug in. So I'm going to go, okay, T is equal to 2 pi. The reason pi is in there is because as that swings, it's swinging at a curve. So pi deals with circles and deals with curves. We'll do more with that next year in geometry. But pi has to do with circles and curves. Then we've got square root of 4.9 over 9.8. So what I would do here, they're just going to want an approximation. So I would probably just use my calculator, and I would start with under my square root there, and I would do 4.9 divided by 9.8, because under that square root, that's basically just like kind of like a parentheses, so you want to do that part first. So I do 4.9 divided by 9.8, and I get 0.5. So now I've got 2 pi and the square root of 0.5 because I just took and divided those. So then from here, probably what I'd do is I'd just do it out on my calculator. So I would do 2 pi. So 2, your pi button, you'll have to use the second for the shift. And then it's the one that's the up arrow just under the clear. So second, and then that button there, pi. You can also always use 3.14, but this is more accurate. So 2 pi, and then times. So you could put a times sign in there. You don't have to. Second, square root of 0.5, and then enter, and we get 4.4288, all that stuff. So I don't know if it tells us what we're supposed to round here to, but let's just round to hundredths. So let's go t is approximately equal to 4.44, and we are measuring this in seconds. Okay, so that is it for your notes. So your book page assignment there is page 604, 18 to 56 even.